Good morning, everybody. Welcome to Hydroc's latest webinar. Good to have your company this morning. My name is Graham Munday. I'm the Marketing Director for Hydroc. Today, we're talking about energy use in buildings. We're looking at all types of buildings, all types of sectors, and we're asking the question, how do we reduce energy? How do you address those goals around net zero and environmental, social and governance goals? And how importantly do we reduce costs for people as well? How do we act now? That's what we're looking at today. Our speaker today, who's going to lead us on this webinar, is Dr. Annie Marston, who's a building physicist. Annie has worked and lectured internationally on the subject and talks on the subject of the performance gap. Let's just say a quick hello to Annie now before we come back to myself. Annie, good morning. How are you?
Hello, I'm very well, thanks, Graham. I'm looking forward to talking to some more students in December at Plymouth University, as well as the ones I spoke to last summer this summer at Howard University. So trying to encourage all those students into the building physics world.
This is fantastic. Great stuff. Thank you. I know Annie speaks, as I say, around the world on this particular subject. Let me just give you a quick flavour of Hydroc if you don't particularly know us and you're joining us for the first time. We are 600 strong, UK-wide. We're an integrated engineering, energy and sustainability consultancy. And briefly, I'm not going to give you any slides on this, but very briefly to kind of give you a flavour of some of the kind of projects and the schemes that we get involved with. We've recently won with our project partners. We've recently won a Best of the Best award at the British Council for Offices, the BCO Awards, for the UK Hydrographic Office headquarters in the southwest of England. This was an award for corporate workspace, a great example of all of our technical disciplines working together and alongside the architects and the contractors, etc. on that scheme, 11,000 square metre scheme. By contrast, and at the other end of the country, our national fire engineering team are working on a major harbourside apartment scheme in Glasgow, where they're advising the construction company there around fire safety, fire engineering, and de-risking issues around the construction of that particular building. And our energy and sustainability team are working across the country and particularly at a very strategic level on a number of big master plan sites. It's a big scheme in Oxfordshire where they're working with a major developer and a major fund to set the upfront sustainability strategy for that entire development. So that kind of gives you a flavour of the sort of diversity of the work that Hydroc is involved with across the company. In terms of today, Annie is going to present to you for around about 25 minutes or so. There is a question and answer box that you will see there, so you can post your questions. I will be able to see those, and we'll take some questions then at the end from there for about 10 minutes at the end. So right now I'm going to pass you to Annie, who's going to talk to you about energy use in buildings. So Annie, over to you.
Thanks, Graham. So yeah, today I'm going to talk about what we can do right now to improve the energy use of our buildings and reduce the carbon emissions into the atmosphere. A little bit about me, if I can get the presentation to move forward. I recently got a GoPro and learned how to open my eyes underwater. So I've been playing a lot with that. And also I was the third person in the world and the first woman to wear that backpack you see there, which is actually a very exciting piece of technology that I won't be talking about today, but feel free to ask me questions about it at some other time. But it's all about going and scanning existing buildings and creating models, and yeah, very exciting stuff. So in general, I've worked in this industry for about 20 years, very passionate about our environment and affordable energy and making buildings work for us. So what can we do right now? I know that often we really focus on the REBA stages 1 to 4, net zero buildings in new buildings, but we actually have an extraordinary architectural history in this country. We have some buildings that have been standing for over 500 years, and so it's not a small, it's not sort of new build issue really. It's what can we do with these hundreds and thousands of building stocks that we have. It definitely doesn't seem as glamorous as building your brand new net zero, wonderfully flashy building, which of course is a lot of fun. But there's a lot of hard work to be done on our existing building stock, and we can actually make a huge difference. And because it's such a large scale, it means that we don't necessarily have to get to net zero on our building stock. Maybe we just reduce it by 30%, 50% energy usage, and that actually makes those incremental differences will make a much larger difference to our world than just that one net zero building. So I think it's a huge opportunity we have, and one we probably aren't looking quite enough at. So where does building physics come into this? I would say building physics comes into everything, and it's brilliant. But so first of all, we've generally been led in the UK by compliance. So it's usually a pass-fail situation for building physics. And that is dictated by national calculation methodologies. So the way we currently look at the energy in existing buildings is generally through EPCs. And what goes behind those EPCs is the national calculation methodology, and that has very strict inputs. So you are very limited in what you can actually do to your building, and that's because this is a benchmark criteria. And so, for instance, if you have occupancy in your building, you can't put the actual occupancy you have in your building. It's set by the NCM methodology, and when those people come and go from that building is also set. So what happens is that it leads to a lot of false assumptions, and those are because they mirror that benchmark building, but those false assumptions also lead to the performance gap. So that's where the performance gap comes from. I think it's often not really explained properly, but it's because we use these benchmark buildings to assess our real life buildings, and our buildings don't operate the same as our benchmark buildings do. So if compliance isn't working, or isn't a design tool, I should say, compliance works absolutely fine for what it does, but it isn't a design tool. You shouldn't be designing to compliance. And I will give an example later on about why there can be some issues with that. There has been some effort to separate out these compliance models from the predicted energy performance models, and those are generally SIBC TM54 and SIBC TM63. And those are predicting energy use at design stage, that's TM54, and making your building work at post-occupancy, which is TM63. An example I'll go through is sort of it's the intention of TM63. It doesn't follow the criteria exactly, but it's close to. So I think building physics is a much more interesting tool and a much stronger tool to help not only understand how buildings work, but to improve the energy usage and get away from that restriction of compliance. So we should be using our building physics to inform the design as opposed to our compliance models to do so. So that includes our EPCs. What this often is referred to as is a digital twin. Now, digital twin is a term that can mean many, many different things at the moment. So we're separating out to say that's a digital energy twin. And what that does is that the model reflects exactly how the HVAC operates, how the controls operate, what the people are doing inside that building, all those kind of things. So it can reflect the operation of the building exactly as it is, so a digital twin with reference to energy. It's all very good, but why are we bothering to do this? It seems like it's going to cost a lot of money, and the tenants aren't complaining. And as we all know, if the tenants aren't complaining, it tends to be quite nice just to leave things as they are and not fiddle with thermostats and so on. So for me, I think it's quite odd because it's rare that we'll let machines we own operate badly like this. I mean, cars are really an obvious example of this. We have for cars, we have to MOT them every year. That's for safety, but then optionally, most people will take them for a service to make sure that they run more efficiently. So if you bought a car and you were told it was going to do 40 miles to the gallon and it was only doing 20 miles to the gallon, you would want to know why. And also you might take it back. And the other thing is, if you had a car and you switched off and it carried on running, you would think, this car is broken. I'll have another one, please. Thank you very much. So why don't we do that with our buildings? Our buildings are much bigger, much more expensive. not that much more complicated than a car, although there is a certain amount of complications to them. So why do we let that happen? We tend to also just change our HVAC or look at our buildings when they have run their term. So maybe 30 years, it's time to pull the boiler out and look at something else. So I think this is really not about making enormous changes to your buildings. It's about, you don't have to replace the facade, you don't have to rip out all your HVAC. You just have to look at take a forensic look at your building and work out what's happening and make it run more efficiently. So again, you wouldn't expect to go to a garage and the mechanic just to say, okay, well, you need a whole new car, whole new engine. This is all rubbish. What you would expect is them to find the broken part, put it in, fix it. Your car's running better. So we're wasting tons of energy and carbon and money year after year after year with our buildings performing badly. We need to service them, get them under control. And it's not about retrofit, it's about the efficiency and the building's potential. Okay, so here's my example. So I'm sorry, all my examples are under NDA. So which means, much to everyone's disappointment, you're going to see a lot of graphs now and not a lot of pretty pictures of buildings. And so I'm sorry about that, but I'm an engineer and I find graphs really easy to explain things. So I'll try to sort of make it a bit more interesting. But so what we had is an office building in London. It was built in the 1970s. It's never had any retrofit apart from what the tenants have done in their spaces. What has happened to it is that some of the controls have been changed over the years in order actually to incorporate what the tenants have done in their spaces. So they just wanted to know, you know, what was going on and what potential savings there might be through controls. So what this graph is showing you here is how the mechanical system is operating in the building. Now, this is our first forensic look. So we look and we say, okay, what energy components are there and what are they all doing? What are the temperatures? What are the flow rates? How are they all interacting with each other? Because one of the things, especially in a commercial office building, is that your tenant spaces often have one thing going on and your central units will have a second thing going on. So what we're looking at there is on the right hand side is a VRF unit in the floors to heat and cool, mostly to cool, and then a central air handling unit to provide fresh air and actually provide hot fresh air as well. And this is what the current status was. Go back in a minute and show you what the other status was. So what we then do is look at what the temperatures are through the air handling unit into the space and which parts of the air handling unit and the space units are using the energy. So in this case, essentially what you're seeing is that the fans are using quite a lot of energy, unsurprisingly. The return air and the outdoor air is mixing together. They're coming in at 16 degrees. That's then being reheated by the reheat coil up to 29 degrees. That's then being cooled down again by the VRF coil in order to meet the 20 degree or 24 degree Celsius that they're requiring that day. So what we're getting is conflicting. Your air handling unit is conflicting with your VRF. And so this is what we tend to find. We look at the forensics and then we see, okay, which parts are conflicting with which. So the first thing we do is calibrate our energy model with the building data. So here is just the calibration. The top is the electricity calibration. The orange sort of lines are the metered data and the solid yellow is the model data. So they're very close. And then the gas underneath, again, the lines are the metered and the solid is the modelled. And then we can break it down into each constituent part. So got the metered data on the left and the model data on the right. So you can see which bits are causing most energy usage. And in this case, it was heating and small power. I don't think that's a big surprise to anyone, but the fans were also using a lot of energy. So we wanted to look at those. There's a small amount of cooling. So we've calibrated our model and we've found that there's some issues. The next thing we do is go in and find all the control points on that system. And I am mad about controls. I think controls are magic, and I know it's pretty niche interest. So they're just magic. So we go in and look at all the controls, and what we found is that actually originally the system was set up as a VAV reheat system, and they turned off the chillers and the cooling towers to save energy because the tenants had put in VRF systems into their spaces. So they'd kind of tried to change the air handling unit to a fresh air only air handling unit, but with heating. So they sort of, it was all a bit of a struggle. And we have lots of control points. So what we did is fixed up those control points and said, if you do this, reduce the airflow rate going through, you don't need so much air going through, increase the heating coil temperature from 12 to 18, take the reheat coils offline, don't need those anymore, and let the VRF do the comfort cooling and comfort heating in the space. So that was our original, as we saw. And then this is how it operates now. So we've got rid of that reheat. So you're not cooling heated air. So you haven't got that conflict anymore. And then also you've reduced your fan energy by 1/3. You've reduced your heating coil energy by 1/3. You've reduced your VRF cooling coil energy by 1/3. You've increased your VRF heating coil energy, which is fine. So overall, you've suddenly got this massive decrease in overall energy because you've switched where you need the units to work, essentially. And this is all controls. We've not put anything new in. We've not retrofitted anything. Now, it's true that this is a very old system, so some motors on the fans might not be working quite right, and we might have to retrofit a few little bits like that to make sure that they can reduce their fan power and things like that. But in essence, it is a controls solution. So just to see what kind of impact that makes, again, remember, this is really only controls. So we've got our first bar is our utility bills. That's what the building's currently using. Our second bar is what the original system was designed to do. Third bar is current operation. So if we change it to a fresh air system only, we save 12% of the energy annually, which equates to £55,000. If we then change it from a fresh air, if we then add in that, turn off all those reheat coils and make that big heating coil go up to 18, we save £70,000 a year. And if we put the a runaround heating coil, so it did have a return duct, so all the air was returned into a plant room. It was just returned into a plant room. It didn't have anything else, but we thought we could duct it in, and a runaround heating coil with about a 50% efficiency, which obviously is a financial input, saves £100,000 a year. Now, if you look at that over 30 years, that's £3 million saving. So even if you're investing in just the heat exchanger, that's an amazing investment. That could be £1 million after 10 years. These aren't insignificant portions of money you're saving. And not only that, you're saving 1/3 of your energy use and carbon output. And this was based on a gas boiler. And as we know, gas prices have just suddenly gone through the roof. So those costs would just, would be extraordinarily higher. So it's not only doing great things for the world, which you are, but it's also saving that money and making the spaces more comfortable for the tenants. Because if you're putting 33-degree air into a space and then cooling it down, someone's going to be sat under that 33-degree air going, this is too hot. And then someone's going to be sat under the cooling thing going, this is too cold. So you've got two tenants that are really uncomfortable in the space. Whereas if you put ambient air in, that person says, oh, there's a bit of a draft, but it's okay. And then the VRF coil doesn't have to cool it down. So the person under the VRF unit is also happy. So it's a whole section of things. It's comfort, it's cost, and it's carbon. So that's just taking a forensic look. That study probably took about 2 months. So it's not an insignificant amount of time, but it's a little bit of time. So we've got, as I said, we've got hundreds of thousands of buildings, and that was 2 months. We can't spend 2 months on each one. So what can we do about that? What can we do about community energy and building portfolios? So a question I get asked a lot of is, how am I going to achieve an EPC rating of C for all my building stock by 2030? Okay, so this is a really common question, and especially from clients with large portfolios of buildings, because it's a significant change and thing that they're going to have to do. And we've got what, 8 years left for that. So it's quite a lot of short amount of time to do it. And right now, I'm sure most of you are aware that Part L, the NCM methodology and EPC, they all have consultation documents out. We've been expecting them to land for quite a few years. They still haven't landed. They will very, very soon, absolutely. And so everything is changing. And so not only how do I get to a C, but one of the answers that we give is we actually don't know what the criteria is even going to be moving forward, but we can make some assumptions, and we have seen the consultation documents at least, and we can look into the data in those. And the other huge change, which we all know, is our carbon factors are updating. And this is also significant because it, is leading to the electrification of a lot of buildings. And so we need to consider that too. So just to look at the carbon factors for a second, because they are important. The carbon factors that we currently use for compliance, for EPCs, for Part L, for any compliance simulation are from 2006, essentially, maybe between 2006 and 2013. So the gas carbon factor isn't changing that much, so we don't have to worry or pay too much attention to it at the moment, apart from the prices. But the electricity carbon factor that we use currently still is 0.519. I don't worry too much about the units. 0.519, it's kilograms of CO2 equivalent per kilowatt hour. Where the grid is right now is at 0.212, so it's over 50% lower for electricity right now. So everyone is putting heat pumps and electrifying their buildings, but actually when you try and do compliance or EPC calculations, they're coming out as only just passing or not passing at all, because the carbon factors they're using are the old carbon factors. So we're expecting these carbon factors to continue to fall as more renewable energy comes online, and we are hoping, or we know that in the new consultation documents, the new Part L and new EPCs will change their carbon factor. We're not quite sure what it's going to change it to. The easiest one to use right now is that the GLA have changed their carbon factors to SAP 10. So those are quite good for predicting out the future, but they're still a little bit higher than perhaps where we will end up. So that's just a bit of context on the carbon factors, because it does make a difference when you're electrifying your buildings, and it's just going to lead to a lot of electrification. So just to sort of step back and look at entire building stocks, there is a process we can use to it's taking that sort of forensic approach but applying it over a large scale project. So what we do is we choose prototypes of buildings, and to represent the building stock, and we model those in detail, in forensic detail, like we did with the original office building. So we have all the controls, all the HVAC in there, so we can say, okay, well, this type of building, if you change these controls, you can do this and this and this. We calibrate them to known utility information. That's very key. So then our models represent that entire building stock, and then we make sure that there's all that detail in them. So you can take that and then you can make changes to your models and say, if you do this, the impact over your entire building stock will be X. So I'll give you an example of this. And I like to say it's how we will change the world. I'm not making any bones about it. I think we can all change the world, and I think this is one of the ways we can do it. So this was a set of hotels. Now I'm just going to come back to the EPC thing again, because when you take a forensic look at buildings, what you notice is the differences between things. So we had some hotel buildings, I think I'm going to say about 150. We ended up making about 9 prototypes, according to age, location, things like that, and heating system. And we found that from the utility data, the hotels were using about 30 litres of hot water per room. And we assumed that they were probably using those between, in the morning mostly, and then maybe some in the evening. So we calibrated our model to our utility data, and what we got was those green bars in that bar chart. So you'll see that our service hot water was the highest usage, space heating and lighting was similar, and then our plug load was quite low. Hotel rooms don't have much plug load, and then our pumps were quite high because we had low temperature hot water systems. So then we said, okay, the client wanted to know how they could get to an EPC of C in 2030. So we said, okay, well, we'll run the EPC on this model. And the energy usage we got out as those orange lines, bars. The service hot water was creating massive energy usage in the EPC model. So, okay, we need to look at why that's the case. What's happening? Why on earth is EPC predicting that they're using so much more water? In fact, they were using 10 times more domestic water than the real life building was. And so what we found was that they said they were using 23 litres per second per hour, and they were following occupancy. Now, obviously in a hotel room, occupancy is through the night. So they were assuming people were showering at 2 in the morning. So it just, when we looked at that, we said, okay, well, EPCs, we don't want to make our decisions on EPCs because this isn't how the building's really working. We want to make our decisions on the operational energy model. I will say that this really shocked our client when they saw the EPCs were doing this, because it's not good. That's all I can say. It's really difficult because the one rating you have to do is your EPC rating. So this is quite a complex tool, but we created a tool for them because we were looking over the whole building stock, but also we wanted to say, okay, well, if you're going to Hotel A, this is what has in it already. These are the cumulative results of putting efficiency measures in. So I'm just going to go over this very quickly. On the left-hand side, sorry, I don't know my left and right, so you have to bear with me on my left-hand side, I think. We've got the current rating of the EPC, floor area, how many beds they've got, and then we've got how the building is currently running. And then we have 3 efficiency measure packages. The first was LED lighting throughout. The second was air source heat pumps to do the low temperature, to do the hot water, domestic and service and heating, space heating. And then the third was fabric efficiency measures. Now, we don't normally see it that way around. Normally we see the fabric measures go first, be lean, be clean, be green. But in this case, it's so expensive to do the fabric measures on an existing building. We wanted to do what are the cheaper measures and how far can we get before we have to deal with the fabric. So at the bottom of that, you have the cost per room, you have the electricity use per room, and then you have the predicted EPC according to 2013, according to our current EPC status. And then I use the carbon factors from the GLA, the ones that currently are in use, the new carbon factors, and did a crystal ball, assuming that they were going to have the same NCM methodology moving forward, just change the carbon factors. And so then we could predict out what the EPCs might be moving forward. And then we did some cost calculations as well. So got their actual electricity costs, gas costs, and then I assumed a price rise of 1% each year on those, and then looked at an internal rate of return if they could get that. So the key thing here is, she'll get to the key message, is that we've got our first, on the bar chart, we've got our first thing is the metered data. That is how much that hotel is using right now. Then next to it, we've got the model data. So that's the prototype compared with the meter data. So we're not too far off. It's all right. They're never going to be very close in when you do the prototypes, but they're good enough to understand what the potential changes might be. Now, if we put LED lighting throughout the building and we put PV on the roof, 100% PV on the roof, covered. Yeah, they've got some car park as well. Their operational energy goes down to 0. And they've got a minus £250 cost a year. But their EPC right now would be a D, and in the future would be a C. So that's why it's all a bit crazy, because they, if you want to invest your money, you get to net zero. But because the EPC, the National Calculation Methodology, has such a high domestic hot water load, you cannot get your EPC down in real life. I mean, you just can't get your EPC down to a level which reflects what you're doing in real life. So it was really interesting, and it was a bit confusing, because then where do you put your money? You have to have an EPC of a C, and luckily in the future case it does look like they can get that C, but they could potentially be operating at net zero and still have an EPC of a D. So this causes a lot of sort of confusion. We've got everything there so you can see what's happening, and that was the reason why we kind of created this tool, so you could see what was going on. And you could see the payback was 10 years on the PV and the LED lighting, and if you wanted your 5% internal rate of return, you'll get that in 14 years. So again, it's looking at the financials as well as the controls and the forensic details. But it was just one of those things where it's like, okay, we really have to be a bit more careful about how we're designing our buildings and what advice we are all giving each other. So if we look at the building stock as a whole, I'll just do the top graph. That grey line there is the metered data, and it's what would happen if you just leave your building alone, according to the decarbonisation of the grid, as we expect it to continue to decarbonise. So you actually just, I think you cut your carbon emissions by about at least a third by just sitting there doing nothing. When you add the LED lighting, it makes a big difference now. It's making a smaller difference as you go on. If you put the heat pumps in and then the envelope measures on top, you can really reduce it down. So I would say that if you put your LED lighting and your heat pumps in, by 2030 you can be looking at a total, and again this is 150 buildings ish. You would then reduce your carbon emissions from, I think, let's say 6,000 tons of CO2 down to 2,500 tons of CO2. So it's properly significant reductions with small incremental changes. Again, it's not this glamorous kind of, yes, we're going to do this one great hotel, we're going to do the whole building stock, and we're going to do the measures that just take the whole thing down. Now, when you look at how much the EPC are predicting the carbon you're using, I couldn't use the same axis values, because the EPC is predicting that this total building stock is using 32,000 tons of carbon, which it just isn't, because we've got the meter data to show it isn't. So you can see what the change would make. The LED lighting makes absolutely no difference to an EPC. So why would people put LED lighting into their buildings if the EPC is showing zero carbon savings, whereas in real life you're saving nearly 1,000 tons of carbon. And the heat pumps are showing good savings. But it was just a really interesting contrast. And again, it's all about making the correct decisions according to what your actual overall goals are. So that is my quick summary of what we're doing. So my conclusions are, what can we do right now? We've got to tackle our existing building stock. That's where all the carbon savings lie. It's not as glamorous, but it is a really good place to start. How can I make a difference? I'm just going to say controls, 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 controls. I love controls. They're magic. You can do so much with them and save so much energy and cost and make everyone more comfortable. And you're not alone. We want to look at operation, not compliance, and we want to use that building physics to inform the design. And I have lofty goals, but I believe we all can change the world. I think we're in a great position in our industry right now that we have so much that we can do to tackle climate change. So I would say use the kind of prototype models, use the forensic, look at your buildings, and you can apply savings over hundreds and hundreds of buildings. If we take that office building, say £1 million saved in 10 years, if you've got a portfolio of 150 office buildings, you're just starting to, I mean, the numbers are just going to multiply out with savings. So that is everything from me. Thank you so much all for listening, and I shall open up to questions.
Annie, thank you so much indeed. That was fascinating. So much information there. We have a few minutes, Annie, in terms of taking questions. I'm going to ask. I'm going to put you on the spot a bit, I think, with a couple myself to start with, and reflect some stuff that's come in here as well. For those like me, maybe, who don't necessarily deeply understand the subject, because you clearly do. The EPCs. So I have to. It just begs the question to me. So what's happening? What's happening with them? On the last, just to set that up a little bit, if you like, the summer holiday, we did a webinar with one of your colleagues, Glenn Irwin, and he talked about whether EPCs were potentially going to be faded out by the government, and he talked about the neighbours scheme that is coming in. Explain to me in just plain language, what it doesn't seem to me like they're working. So what can be done?
You're right, they don't seem to work very well. I mean, at the moment, what we do with EPCs is we take an imaginary building and compare them against that imaginary building. Now that, as we've seen, doesn't work very well. And so there is a push now to use the neighbours scheme, which is based on actual operational energy. And I think that's where we'll move forward. There in the Part L, there is now prediction of operational energy, and then looking at metering, monitoring as we go forward. And really the best way to show how a building is improving its energy is by reporting year on year and showing that you're actively making changes to it. So I think the EPCs worked for what they were to begin with, but I think now their time has come to maybe move on and find a better way to measure an existing building, and especially when people do put a lot of effort into making their buildings better and they can't change their EPC rating. I think that's not a great. It's a bit demoralising, I think. So existing metered data is what we need.
Okay. Now, Ludmilla from the BRE has messaged and said quite a lot. Annie, can you see these on your screen at the moment as well, if you do the Q&A bit? Because I'm going to publish these for the audience, but there's a fair bit from Ludmilla here. Is asking about energy assessments have very different purposes. I'm going to publish these a bit at a time as I go. Energy assessments have very different purposes. Design, building regulations, compliance, EPC, which is intended for comparing buildings, we just talked about it, retrofits, sizing of heating systems, and NCM has its own purpose, producing EPCs and regulations. It can't cover all possible purposes. So there appears to be a bit of a mismatch. Yes. I don't know whether you have a view on that.
Yes, I think compliance is absolutely brilliant for compliance. I think the thing that's happened is that we just use building physics for compliance and we use it to lead our design decisions. And I think that's where it's gone wrong. So I absolutely agree that there are reasons why we want to use compliance, and comparing things to benchmarks is great, but we just shouldn't be making decisions on that. We should be using building physics for what it is. It's a design tool. It's supposed to reflect what the building's doing, and then we take compliance out of that, as opposed to the other way around. And I think that's really all I'm really passionate about, is we have to stop using compliance as a design tool, because that's not its purpose.
Yeah, okay, thank you. And that was a very key message from you at the start of your session as well. Josh has posted a question here. You mentioned it's not about retrofit, it's about efficiency and potential. Does the PAS 2035 retrofit therefore not go far enough, in your opinion?
So it's not. Sorry, I probably was a bit too firm on controls. It is about retrofit as well. But what I think it is we go so quickly into retrofit that we don't actually manage our buildings properly. And what my thinking is, we just need to take a step back and think for a little bit. Think about the building. Again, it's that same thing as a car or a washing machine. You don't immediately fit a part just because you think that's going to make it better. You make it work first, and then you say, okay, what's the next step? So I would say that the controls do that, make your building efficient, and then from that you can see where the best retrofit lies, because it might not be where you first think it is, especially with that office building. When they turned the chillers off, it was a good thing, but actually what they've done is created a problem within the whole building, because that you then had conflicting controls, which you don't want. So
Annie, I'm going to put you on the spot again and ask the question, and we're going to wrap up in a second. I mean, the office example you gave was fascinating as well. So whose responsibility is that? I mean, it's nobody's fault in a way that over time the building gets used in different ways. People come in, do their own fit out, move out, etc., and people make these decisions. But what you do is, as you've said, is that forensic analysis. And in the world that we're in now, suddenly you realise what actually a big impact that's having. So who do we need to help? Who needs to stop for a second and say, hey, we do need to do a proper analysis of everything that's going on here?
So it is really hard because there are so many people involved in buildings. I think that's where the complexity lies. It's not like when you have a car and there's one owner and you are responsible for it. So I think the first stop is any building owner, because you are responsible for generally the central services and things like that, when we can make those better, even without touching the tenants side of things, although they might be interested as well. Facilities managers, whenever facilities managers are coming across problems, if there's problem after problem, complaint after complaint, it might be time to just step back and say, right, let's actually just take the whole thing. And then people that manage campuses, building portfolios, all those kind of bits and pieces. And then if you're a tenant, why not sort of start questioning things? It even go as far as your own home. Just go and check the controls in your own home. Are you leaving lights on? Have you got your thermostat on for all the hours? I'm not saying don't be comfortable, absolutely be comfortable, but are you leaving the heating on overnight? Like, have you, just because you can't be bothered to go and change the thermostat? I mean, it's little things like that. Just make sure it's not wasted, like waste the energy. Yeah, so mainly building owners, I think at this point, facilities managers are the ones that really have the ability and the power to come in and go, right, let's sort this out.
Yeah. And it's those little things scaled up to this level that make a heck of a difference, of course. Okay, Annie, thank you so much for your time today. Absolutely fascinating, as always. We're going to wrap up there. I'm conscious everybody has very busy days and diaries. Thank you so much for your company today on this webinar. We will share a link to this later on as well, and it will be on our website. Just a quick flag for an event that's coming up on the 4th of November. We have our fire engineering team doing a session on the electronic golden thread. The golden thread in fire engineering and fire safety design is a big topic at the moment, and Chris Chanel from our team in Newcastle will be leading that particular event on the 4th of November. We will share details on it. Equally, if you're sat there now thinking, gosh, I really want to know about that, you can email us at events@hydrock.com, and myself and the team will see that and make sure that we do get those details to you. But thank you for your company today, Annie. Thank you as well, and I hope you have a great day. Thank you.